If you've ever watched birds fly, you may notice that not all birds are built the same. Some can glide for hours with very little effort. Some use the wind itself to stay aloft. Some rely on steady, powered flight. And some are built for speed. Humans do the same thing in our flying machines. Some aircraft are designed to glide efficiently for long periods of time. Some are built to maximize efficiency in moving air. Some rely on continuous engine power. And some are built for speed. We design aircraft to solve the same problem: how to move efficiently through air. When you group birds by how they fly, you start to see something interesting. The same wing designs show up again in aircraft for the same aerodynamic reasons. There are 4 major wing strategies we'll look at: passive soaring, active soaring, elliptical wings, and high-speed wings. Passive soaring wings. Passive soaring birds include vultures, condors, and large eagles. These birds rely on rising columns of warm air called thermals. Instead of flapping continuously, they circle inside of these thermals to gain altitude, then glide on to the next one. Because of that, their wings are broad and relatively long, with slotted tips that help reduce drag and increase lift at low speeds. Aircraft designed for low-speed flight use the same idea. Gliders and bush planes have large wings with high lift and low stall speeds, allowing them to stay airborne with minimal power. Both designs prioritize lift and stability rather than speed. Active soaring wings. Active soaring is most famously used by albatrosses. Unlike passive soaring, this strategy doesn't depend on rising air. Instead, it uses wind gradients over the ocean. Wind moves slower near the water's surface and faster higher up. By repeatedly flying between these layers, the birds gain energy from the difference in wind speeds. This is called dynamic soaring. To do this efficiently, albatross wings are extremely long and narrow, giving them a very high aspect ratio. Aircraft designed for long endurance use the same shape. High-efficiency gliders and long-range drones have long, narrow wings that reduce drag and allow sustained flight with minimal energy input. These wings aren't good for maneuvering, they're built for efficiency. Elliptical wings. Elliptical wings are common in birds that rely on steady flapping flight, such as swallows and many seabirds. This wing shape distributes lift evenly across the span, which minimizes induced drag during powered flight. One of the most famous examples is the Supermarine Spitfire, which used an elliptical wing to maximize efficiency under engine power. This is one of the clearest examples of nature and engineering arriving at the same solution independently. High-speed wings. High-speed birds such as falcons and swifts have narrow pointed wings. These wings reduce drag and allow for fast flight and steep dives, but they sacrifice low-speed lift. Aircraft designed for speed follow the same principle. Jet aircraft use shorter, more narrow, and often swept wings to remain stable at high velocities. As speed increases, drag becomes the dominant limitation, and wing shape shift towards minimizing resistance rather than maximizing lift. Passive soaring, active soaring, elliptical wings, high-speed wings. Each wing type reflects a different flight strategy. Passive soaring uses rising air, active soaring uses moving air, elliptical wings optimize powered efficiency, high-speed wings prioritize velocity. Birds and aircrafts don't look similar by coincidence. They look similar because air only allows a limited number of efficient solutions. Different designers, evolution, and engineers working under the same rules. Physics. This is Alex Warden. Thanks for watching.